Welcome to a discussion of the Walnut software. Walnut is the controlling software used in the FPath project. And what is the FPath project, you may ask? Well, FPath is an open-ended investigation into the Feynman Path to nanotechnology. Basically, it is the idea that large tools make smaller tools, which make smaller tools, and so on, until you reach a point where you can move atoms about wherever you wish. Of course, FPath is nowhere near that just now. It is still operating on the scale of centimeter, but you have to start somewhere. Please note there is a link to a web page write-up of the FPath project in the comments below. The way I see it is that there are two ways to approach the FPath problem. Either you can make your machinery extremely precise, or you can accept imprecision and have control compensate for the problems. The first option is the route the semiconductor industry has taken: insanely precise machinery reliably doing exactly what it is told to do. The problem is that precision costs, and extreme precision costs big. A semiconductor company has that sort of money, so no problem for them. The FPath project is intended to be an inexpensive approach, and since low-cost material will be used, problems such as leveling, backlash, and play must be compensated for. The way I've chosen to do this is by creating a very adaptable closed-loop control mechanism. This closed-loop control mechanism is the Walnut software. For those who are unfamiliar with the concept of open-loop versus closed-loop control, here is a brief digression. I apologize in advance for the poor quality of the graphics. I am not a graphic artist. Say you have a target. It has a coordinate. Let's call it x equals 0, y equals 0. Now here we have a motorized tool we wish to move to the target point. Let us assume it is at the point x equals 2, y equals 2. In an open loop control system, we simply say move to 0, 0 and assume it gets there. In a precision system, we can simply assume that it does. Not so if the tool is built from non-precision components. If we tell it to move to the point 0, 0, we might actually move the tool to x equals 0.3 and y equals 0.2. This gets even worse as we try for repeatability, as the errors are cumulative. If we move back to the coordinate x equals 2, y equals 2, then we might end up at 2.4, 1.8. Moving back from that point to 0, 0 gives us even more error. All tools have imprecision. It is just that in an effective open-loop system, the precision is such that the errors are kept so small they do not matter. This is how some desktop printers work. One problem with this approach is that things like unpredictable errors are hard to detect. For example, if you carefully induce some slip into a paper feed, you might be able to prevent a printer's paper jam detection mechanism activating, and the printer would cheerfully continue. The page would come out as an overprinted mess. The printer has no real way of knowing that error in the paper feed exceeded its assumed maximum level. In summary, in an open-loop control system, the results of any actions taken are not known to the controlling entity. This is okay if the accuracy of the machinery is acceptable. In a closed-loop control system, things operate differently. It has feedback. Let's look at the same situation. Again, we wish to move a tool from point x equals 2 and y equals 2 onto the point 0, 0. As we move from the start point, we continuously assess where we are and what we are doing. We don't really care about absolute coordinates. We just know we are getting closer in the x direction and the y direction. We carry on moving, and when we reach the point we think is 0, 0, we can see that we have errors, so we simply keep going, doing what is necessary to make the outcome what we want. Eventually, we reach the goal. Moving back to the start point is similar. We continuously apply adjustments until our tool reaches the point we wish. Continuous feedback has effectively removed the errors introduced by the inaccurate machinery. This opens up all kinds of possibilities, such as using much less expensive tooling, hitting moving targets, or adjusting the speed of the approach to avoid overshoot. Things like PID control are also possible. Hopefully this will clarify the design choices for the Walnut software. Since the intention of the FPath software is to have tools build smaller tools, the use of a closed-loop control system can dramatically reduce costs and remove a lot of errors. If the essence of a closed-loop system is feedback, how then do we provide this feedback? Well, clearly you need a position sensor that will continuously report on the location of objects of interest. There are lots of different sensors, but the most familiar to us is optical. This is how you would do it if you were manually operating such a system. Let's draw a camera and the bed containing the objects of interest. We are looking edge on here. Again, I apologize for the poor quality of the graphics. The camera in my setup is a common Logitech C920 USB camera. It is looking down at the bed. If we have a USB camera, we have to have something to plug it into and interpret that image. So let's draw in a PC running Windows 10. The Walnut server software runs on the PC, and it contains quite sophisticated image recognition code to identify objects and their position. More on that later, but for now let's continue with a broad brush overview of the system. In a simple example, let's assume that the Walnut server software has figured out the coordinates of a static and dynamic object and wants to move the dynamic object onto the position of the static object. For this to work, the PC has to be able to send physical signals to the motors controlling the objects on the bed that the camera is looking at. This is a surprisingly complex process and involves a lot of decisions and electrical control. I'm talking about streams of carefully phased on-off steps for stepper motors or controlled pulse widths for DC motors. The PC already has enough to do just recognizing objects and making decisions about them. Also, interfacing with electronics is really not a PC's forte, so we delegate this responsibility to a microcontroller. The microcontroller I have chosen to use is called the Beaglebone Black. I could have used others, such as one of the many Raspberry Pi models, but the Beaglebone has several interesting features that make it a really good choice for this role. I will talk more about that in a subsequent video. So, let's draw in a Beaglebone Black running Linux. Of course, the PC needs to talk to the Beaglebone Black. How can this be done? Well, there are all sorts of methods, but both the Beaglebone Black and the PC can natively communicate via TCP/IP over Ethernet. So let's just draw in a Cat5 Ethernet cable between them. Once the two devices can talk to each other, we need something running on the Beaglebone Black that can accept and process the data. This is the Walnut client software. The software running on the PC is called the Walnut server software. The Walnut client can accept data from the PC via TCP/IP, and it can use that data to control its various I/O lines in order to move things about. But wait, once we want to move things about, we're starting to talk power. It's not enough just to turn a signal on and off. In order to move motors, you need to turn power on and off in a carefully synchronized way. There are plenty of devices out there designed to do just that. These are called motor driver boards. So let's further delegate responsibility for moving the motors to those. We now draw in some motor driver boards. These can accept signals from the Beaglebone Black and actually move the motors. The signals in this case can be such things as step and direction for stepper motors or pulse width modulated signal and direction for DC motors. So let's draw in some of that cabling. We continue on to draw in the motors and some cabling for them. You can see what is going on here at a macro level. The camera sees the objects on the bed. The PC interprets the image string and figures out what component is where and makes overall decisions about what actions to take. It then sends these decisions to the Beaglebone Black. The Beaglebone Black accepts them and figures out what it needs to do and then generates the I/O signals appropriate to the type of actuators on the bed. These signals are then sent to the attached motor drivers, which convert them into power signals suitable for actually moving the motors and actuators. Once things are moving, the camera sees the change in target location. The PC interprets the new positions and tells the Beaglebone Black this new information. The Beaglebone Black adjusts the signals to the motor drivers, which then change the behaviors of the motors appropriately. All of these events happen continuously and in real time. It should be noted that besides camera data, it is also possible to send other signals to the PC. The Beaglebone Black can accept signals via its I/O ports or its A to D converters and transmit those signals back to the PC via TCP/IP. This enables the system to utilize the absolute multitude of sophisticated I/O options on the Beaglebone Black to acquire additional information. This is a big improvement over having to try to figure out how to interface such things to the PC directly. Let's draw in a few of these signal lines now. Well, that's a broad brush overview of the Walnut software. It is a closed-loop system consisting of multiple parts, each of which plays a role in the continuous adjustment of the system output. It is the constant feedback and adjustment that reduces the error, even though the components themselves are not especially precise. Clearly there is a lot to unpack here, but this video is getting kind of long. Please see the next video in this series for a more complete discussion of each specific component in the Walnut software.